Hello everyone, I'm Pengtao here from CMU. Today I'm going to introduce our recent work on diversifying restricted for document modeling. This is joint work with Yuntian, Deng, and Xing. Document modeling aims to discover the latent semantics and topics such as politics, and food from the document collection and represent the documents into this.
Doesn't work so well. You still need to use. You can turn around just facing.
To represent the documents into this latent semantic space, compared with backwards representations, these semantic representations can be more effective for downstream text mining tasks, such as document retrieval, classification, and clustering. There have been many models proposed for document modeling, such as the directed topic model, latent dirichlet allocation, and undirected topic model, such as the restricted Boltzmann machine and neural network, and many others. In this work, we are particularly interested in RBM for two reasons. First, it has shown great success in modeling documents. Second, it is very efficient in inferring the latent representations at the test time, which is crucial for applications that has real-time requirements, such as document retrieval. But the techniques developed in our work can be also applied to other latent variable or latent space models, such as LDA and neural network. Restricted Boltzmann machine is a two-layer undirected graphical model. When applied to modeling documents, the hidden units are used to model the topics, and the visible units are used to model the observed words. The hidden units are connected with the visible units with undirected weighted edges, which are used to characterize the interaction between topics and words. Each hidden unit has a weight vector connecting to all the visible units. RBM define an energy function over this graph topology, and which induces a probability, and the weight vectors can be learned by maximizing the likelihood function. In many text collection, the popularity or frequency of topics is distributed in this parallel fashion, which means that a few topics in this gray region called dominant topics occur very frequently, while most of the topics in this yellow region, which are called long-tail topics, have very low frequency or probability. For example, thinking about in a news corpora, several topics like politics or economics, sports occur very frequently, while most of the topics such as garden, furniture, and flowers are rarely mentioned. Due to this skewness of topic popularity, the standard RBM is insufficient to capture the long-tail topics. Here we have an illustration where we use the circles to denote the true topics behind the documents, and the triangles to denote the hidden units of RBM. And the size of the circle is proportional to the popularity of a topic. Because each of the long-tail topic is weak signal that contribute little to the likelihood function of RBM. So it is not rewarding for RBM to model them, so it just ignores them. On the other hand, the dominant topics denoted by the large circles, they are the major contributors of the likelihood function, so RBM prefer to use many hidden units to cover them as best as possible. However, these long-tail topics are very important, and they cannot be simply ignored. First, although each long-tail topic has low probability, the total amount of the long-tail topics is huge, so the total probability mass in this long-tail region is large as this dominant region, which means that the long tail topics actually carries the same the information as important as the dominant topics. In many applications, it is the long tail topics can be arguably more interesting than the dominant topics. For example, thinking about using the learned topics for advertisement. In this case, a loose weight topic is more important than a time topic in improving the click-through rate and making profits. So in these applications, it is more interesting and important to capture these long tail topics. So in this work, we basically want to solve this problem and enable RBM to be able to capture these long tail topics. The approach we take is to diversify the hidden units in RBM to make them to be different from each other and diversely spread out to cover not only the dominant topics, but more importantly, the long tail topics denoted by the small circles. The basic intuition is, with diversification, we can spare some hidden units that are originally allocated to the dominant topic and reallocate them to the long tail topics. So think about a process of allocating hidden units to topics. In the standard RBM, suppose the first hidden unit is allocated to a dominant topic. For the second one, it is very likely to be allocated to the dominant topic again to ensure that this topic is sufficiently covered. With diversification, similarly, the first one is allocated to the dominant topic. And for the second one, because of this diversity regularization, the second hidden unit is made different and pushed far away from the first one, so we get a better chance to cover the long tail topic. That's basically the intuition of this diversification method. Based on this motivation, we propose this diversity regularized RBM with the goal to encourage the hidden units to diversely spread out to improve the coverage of long tail topics. The approach we take is we first define a metric to measure the diversity of the hidden units. Recall that each hidden unit is characterized by a weight vector. So actually, we are trying to diversify the weight vectors of the hidden units. And after we define this metric, we can use it as a regularizer to regularize the learning of the hidden units to make them to be diverse. So to define a diversity metric over a set of vectors, we first measure the dissimilarity between two vectors. We want this dissimilarity measure to be invariant to scaling, translation, rotation, and orientation of the two vectors. Commonly used dissimilarity measures such as Euclidean distance or L1 distance are not good because they are sensitive to scaling. Cosine similarity is not ideal either because it is sensitive to the orientations of the vectors. So in this work, we choose to use this non-obtuse angle. If the angle between two vectors is acute or right, we just use it as the dissimilarity measure. If the angle is obtuse, we choose to use the complementary angle of the original angle as the dissimilarity measure. This non-obtuse angle is invariant to scaling, translation, rotation, and orientation of the two vectors. Mathematically, the non-obtuse angle theta between two vectors x and y is defined in this form. After we get this pairwise dissimilarity measure, we can measure the diversity of a vector set. Basically, we take theta ij, which is the non-obtuse angle between vector ai and aj. We take all the pairwise angles. After we get this, we take a mean of all the angles and minus the variance of the angles, which is the diversity matrix of the vector set A. The mean is a summarization of how these vectors are different from each other on the whole. If the angle is large, that means the vectors are different from each other in general. The variance term is used to encourage the vectors to evenly spread out. Basically, we want to avoid this case in the first graph that two vectors are very similar to each other, and the third one is quite different. If you compare these two sets of vectors, they basically share the same mean of pairwise angles. However, in this case, the variance is much smaller. And this case is preferred because these vectors are evenly spread out to different directions. After we get this diversity matrix omega A, we use it to regularize RBM. The first term, LDA, is the original loss function, likelihood function of RBM, and omega A is the diversity matrix. Lambda is the trade-off parameter. This formulation is straightforward. The major technical difficulty is how to optimize omega A, which is non-smooth and non-convex. So to make the optimization easier, we did a little bit reparameterization of the weight vectors A. Basically, we decompose each vector AI into two parts, AI tilde, which is the direction of this vector, and its norm is 1, and the GI, which is the magnitude, the L2 norm of AI. Under this decomposition, we can rewrite the original diversity regularized RBM into this form, which is defined over two sets of variables, G and A tilde. We can optimize G and A tilde alternatively. Fixing A tilde, we optimize G with projected gradient descent, which can be done very efficiently. In the next step, we fix G and optimize A tilde and iterate this process until convergence. For this subproblem, fixing G, optimizing A tilde, omega A tilde is still non-convex and non-smooth. To solve this problem, we derive a lower bound of omega A tilde, which is a smooth function, so we can optimize this lower bound instant and use a gradient method. Regarding how this lower bound is derived, you can check our paper. A nice property of this optimization solution is it turns out that maximizing this lower bound with projected gradient ascent can increase this diversity matrix at each iteration. The idea to prove this is recall that the diversity matrix is composed of two terms, the mean and the variance. So we separately prove that maximizing the lower bound can increase the mean and reduce the variance. So in together, at each iteration, we can increase the diversity matrix. Here is a geometry interpretation why optimizing this lower bound with gradient method can increase the diversity matrix. It turns out that the gradient of the lower bound with respect to a weight vector AI is in the orthogonal complement of the space spanned by all other vectors. Say in this example, we have three vectors, and suppose we are interested in the gradient of this. These weight vectors are denoted by black arrows. Suppose we are interested in the gradient of this weight vector. According to this lemma, its gradient is orthogonal to the other two vectors. So if we take a gradient ascent step of this vector along its gradient direction, we move it here, which is denoted by the blue arrow. You can see that the angle is enlarged. So that's basically the intuition, a geometry interpretation why maximizing this lower bound can increase this diversity matrix. We performed the experiments. over 3 text datasets, we learn the latent representations with the diversified RBM. Then we apply the representations for document retrieval and clustering. We compare with a bunch of baseline methods, including the bag-of-words representation, the directed topic models, and the neural network-based approaches, and also the undirected topic models, the RBM. For retrieval, we use the precision and 100 as the evaluation method, and for clustering, we use accuracy. Here is the retrieval results on the 3 datasets. The x-axis is the number of hidden units. The y-axis is the precision, and the 100, the higher the better. The blue bars are the RBM results without diversification, and the red bars are the results with diversification. You can see from the plots that with diversification, the performance can be dramatically improved. For example, in the first dataset, TDT, with 25 hidden units, we can improve the precision from 10% to around 80%. And on the other datasets, we observe the similar significant improvement. This demonstrates that this diversity regularization is indeed effective in improving the representation power of RBM. A nice thing is that, for example, in the TDT dataset, with 25 hidden units, we can achieve 80% accurate precision. But in the RBM case, even with 500 hidden units, it cannot achieve such high precision. So that means we can pretty much use a lower dimensional representation to perform high performance retrieval. This is very crucial for applications like retrieval, which has real-time requirements. We compare with the baseline methods. Our method, DRBM, achieves the best performance on the TDT and 20 news dataset, and the performance is comparable to the paragraph vector on the Reuters dataset. This is the results on the clustering task. We observe the similar behavior that with diversification, the performance can be significantly improved. This is the comparison with the other methods. Our method achieves the best performance over 3 datasets. To corroborate whether this diversification idea can indeed capture the long-tail semantics or topics, we break the improvement down to different categories. So here, this region is the long-tail region because the number of documents is small. You can see that the relative improvement of RBM is very significant in this region. So that means the diversified RBM is indeed able to capture the long-tail semantics. Due to the time limit, I'm happy to take questions.
Okay, so we have time for one question.
So what would happen if you increase to 1,000 hidden units? Is restricted Boltzmann machine will be just as good as the diversification?
As you can see from the plot, increase the hidden units, the performance of RBM is increasing. So we didn't try.
The question is, if you go for 1,000,
yeah, we didn't try to.
Maybe it asymptotically reaches to the diversification.
Is it possible to get a high precision with 1,000 hidden units? But in that case, the dimension of the representations is too high for this kind of task like retrieval.
So the optimization would be harder, or?
I mean, after you get the representations, it's very hard to do retrieval over feature vectors with 1,000 dimensions.
The other question is the RBM optimization cheaper than the diversified version?
So the basics, the algorithm is gradient descent. RBM using a contrastive divergence, which is essentially a gradient method. So our method is also gradient method. Yeah, the only difference is to compute gradient of omega A. Yeah, not too much complexity.
Okay, so thank you.